probably needs much of an introduction. We're very happy to have Dalang from EPFL, and he's going to talk about, an empty slide, something about the Anderson model.
Okay. Maybe I should have left this slide up. Okay. Well, thank you very much for the invitation. It's certainly a pleasure to be here and to talk to people, and also to enjoy some uninterrupted work time, which is hard to get when you're in your home department. So I'm talking on intermittency properties of the hyperbolic Anderson model, a hyperbolic Anderson problem. So this is joint work with Carl Mueller, but it's also based on a joint paper with Carl Mueller and Roger Tribe, which is sort of one of the key ingredients to the whole piece of work anyway. So I just listed both co-authors. Well, so I'm going to try to use all three projectors if this actually works. Let me begin by reminding you of something that's very well known, which is not directly mentioned in my title, which is just the classical Feynman-Kac formula for the heat equation. So here we just have the heat equation du dt equals half Laplacian plus a potential V of Tx times the solution U of Tx with a given initial condition. And so it's well known that under appropriate conditions on V and the function f, we have this Feynman-Kac formula, which sort of gives a representation of the solution in terms of an average over a functional of Brownian paths. And so, the formula is written here. This is a classical formula. I have this little picture that I hope will become visible, which says if I want the solution at position x and time t, I simply start a Brownian path at that position, run it backwards in time until it hits the origin, and then I evaluate the functional that's inside the expectation and average over many such paths. Okay, so this will be a key ingredient in the work that motivated our work, and a variation on this that will come a bit later. So now I come to what motivated our work, which is a more classical Anderson model. And we started with this paper of Carmona and Molchanov, so it's in the Memoirs of AMS. And in that work, they replaced the deterministic function V of Tx that appears over here on the right with a Gaussian random field f dot of Tx. And so this Gaussian random field is white in time, and with a spatially homogeneous covariance. The space variable could be discrete or continuous. Most of their work was with the discrete space variable, so x and zd. And one thing that they did was study moments of the equation. So the pth moment, expected value of u of Tx to the power p, call that mp of Tx, and the behavior of these moments as t goes to infinity. So most notably the exponential growth, or moment Lyapunov exponents, which are these gamma sub p's that are listed here. So take the log, divide by t, let t go to infinity. And so they showed that these gamma sub p's existed. And they defined a notion of intermittency, or intermittency of order p. And so that's the notion that is written here. So some of these gamma p's might simply be 0, maybe the first p minus 1 of them. And then you might have gamma p, which is strictly positive. And when that happens, these inequalities here, gamma p over p, strictly less than gamma p plus 1 over p plus 1, etc., occur. So the later moments would then also be positive, strictly positive. And so this is a notion of intermittency, and it has some physical meaning, which is not immediately clear from the definition.
Robert, are these dependent on x or independent, the gamma p?
Well, if you start with a constant initial condition, which is what they did, and you have a spatially homogeneous noise, then it would not depend on x.
So somehow you suggest as if p was a natural number here, but of course p can be
P could be anything, and here it's an integer actually.
In integer, but
Yes.
do you always, so you not always get 0 for some integer P minus 1?
No, I'm saying this could happen. It could be that for P equals 1, you already had a strictly positive value. But they say if the solution satisfies this condition, then it's called intermittent of order P. And so the motivation, physical interpretation that they have, which is not at all clear from the definition, is that when this situation happens, the solution is a sort of very small most of the place and has very high peaks in a few places. Okay? So that's not at all clear from this, but that was sort of the physical idea that they had in mind. And then this was later made precise. So I think this has now been made rather precise in this paper of Cranston and Molchanov. And I've listed other papers where this is studied, refined, also almost sure Lyapunov exponents of sample path behavior and not just moment Lyapunov exponents. So there's been many extensions, and this picture of high peaks has been made rather precise. So how far apart are the peaks and that sort of thing. And since moments come in and expectations, you can imagine that the Feynman-Kac formula that I mentioned initially is an important ingredient. And in fact, their analysis of moments was essentially based on the Feynman-Kac formula for the heat equation. And I'm going to be interested in this for the wave equation. We also spent a little bit of time looking at what exists for other kinds of equations, so probabilistic representations of solutions to other PDEs. And there's this very old paper of Mark Katz who studied the telegrapher's equation. So that's space dimension 1. It's essentially also a damped wave equation. And you find other probabilistic representations of solutions to various PDEs that are not quite the Feynman-Kac formula, but sort of extensions or variations on that. And I've listed some papers here that I found. There's a paper of Lejean and Snitman, which does this for the Navier-Stokes equation in R3, so in the whole of R3. There's work on probabilistic representations of solutions to the Boltzmann equation by Sylvie Méliard and several of her co-authors. And there's this paper of Blumker, Romito, and Roger Tribe, also on the probabilistic representation of a solution to a nonlinear heat equation. So the Feynman-Kac formula is a key ingredient in the work of Carmona and Molchanov. And what we wanted to do was look at this for the wave equation. Oops. So the wave equation I've written here. So instead of having the first derivative in time, we have the second derivative in time. Other than that, we keep the same form on the right-hand side, which is solution U, multiplied by a potential V of Tx. Since it's second order in time, you need two initial conditions, the initial position and the initial velocity. And I'm going to be considering this equation in dimensions 1, 2, and 3, spatial dimensions 1, 2, and 3. And so what we want to do is sort of pursue the same program that was developed for the heat equation, beginning with Carmona and Molchanov and the other references that I mentioned. So first, we'd like a sort of probabilistic representation of the solution, which will be analogous to the Feynman-Kac type formula. And we'll actually get a rather general formula that applies to the wave equation, to the heat equation, and to a large class of equations. And then we'd like to replace the V of Tx, potential on the right-hand side, by a Gaussian random field, study moments, so get formulas for moments, and see if these moment Lyapunov exponents exist and have this behavior that was identified for the heat equation by Carmona and Molchanov. Okay, so that's the plan: probabilistic representation, study of moments, and then finally intermittency properties. And so let me begin by telling you the class of partial differential equations that we will be able to handle. So consider a partial differential operator L with constant coefficients. So this could be the heat operator or the wave operator. And what we want is a property of the fundamental solution of this equation. So we want it to be a signed measure with total variation mass to be finite. Okay? So this occurs in many examples. For example, in the heat equation, in any space dimension, L is d over dt minus a half Laplacian. And then the solution is essentially just the fundamental solution is given by the Gaussian density. So the total mass would simply be 1. The condition would be satisfied. If you take the wave equation in dimensions 1, 2, and 3, you have explicit formulas for the fundamental solution. It's not only a measure, but a non-negative measure. And the measure is getting a little bit less regular as the dimension goes up. So in dimension 1, the measure has a density, bounded density, discontinuous, but still bounded. In dimension 2, it also has a density, but that goes to infinity at certain points. And in dimension 3, it's a singular measure, which is supported on the surface area on the boundary of a ball of radius t. In all cases here for the wave equation, the total mass is simply t. So again, the condition that I had at the beginning, the condition here is satisfied. So our formula will apply to all these equations. And let me just mention that it won't apply to the wave equation in dimensions 4 or more because the fundamental solution is not a signed measure. It would apply to the wave equation with damping, again in dimensions 1, 2, and 3. And here that's in part because you have explicit formulas for the fundamental solution. It would also apply to this other equation, which is sometimes called the beam equation. So the operator is d over tt plus Laplacian squared on Rd. So that would also be a situation in which our formula will apply. And so one property that's in common to the Anderson models, be it the heat equation or the wave equation, I mean, in principle, you can write the partial differential equation as an integral equation. And this integral equation is particularly nice because it's essentially linear. That is, you have the solution u here, solution u comes back over here, you integrate u times the potential against the fundamental solution, and then you also have this term w, which is just the solution to the homogeneous wave equation with the appropriate initial conditions. So the same initial conditions as you were putting on u. Okay, so this is a nice formula because it immediately gives you a series representation in the sense that you can sort of iterate this equality, which is the form u equals w plus t of u, where t of u is this integral operator here on the right. And then the u that's inside here, you just replace again by w plus t of u. And you iterate this, and it gives you, well, first of all, a sum, a finite sum. And if the remainder term, if you can show that that goes to 0, you get a series representation. So that's sort of the nice feature of this linear noise. So you have u times noise, or u times a potential, is you immediately have a series representation for the solution.
Excuse me, can I ask you said that you consider LU equals what? LW is 0, but you consider an inhomogeneous problem for u. So it's...
So LU is u times v. LU equals u times v.
And so the S is whatever you get by solving the equation.
The fundamental solution of the equation. Like the heat equation, the fundamental solution will be the Gaussian kernel. Okay?
Your goal is to replace LU equals u times v by LU equals u times f dot.
Exactly.
Okay.
Exactly.
That would be
Well, I'll come to that sort of issue a little bit later. Of course, yeah, then you have to say which integral. It will be an Etos type integral. So just making a little precise, this idea of series representation. So here's a formal statement. Well, the usual assumptions on V and W, V has to be, say, Borel, or maybe bounded or continuous. So, you know, you can have simple assumptions on V, and then you define, so this process of series representation is sort of iterating. You have t and then t squared and so on. So this gives you sort of iterated integrals. So you're defining the m plus first term in terms of the term number m with your integral operator, which is this operator t. And so you can just check that the integral equation has a unique solution, which is given by this series representation, and there's uniform convergence on 0t times rd. Okay, so that's just making precise the idea of series representation. And now I'd like to come to the probabilistic representation. But it's just to say that there is a representation by this series, which is not probabilistic, but which is going to be useful anyway. So here's the idea. So I need certain random ingredients, right? In the standard Feynman-Kac formula, the basic ingredient is Brownian motion. Here the basic ingredient is going to be a process x tilde t, which starts at 0, and all I'm going to require is a condition on its marginal one-dimensional distributions. So essentially I'd like the law of x tilde t to be given by the fundamental solution, which is not quite a probability measure, so you have to normalize. And when it's a signed measure, you have to put the total variation measure here. But say for the heat equation or the wave equation in dimensions 1, 2, and 3, you would just have the fundamental solution on the numerator and either 1 on the denominator for the heat equation or t for the wave equation. And in many cases, such as the heat and wave equation, you don't really need this minus sign that's present, so might as well ignore that for the purposes of the talk. And so this is easy to do in the examples I've given. For example, for the heat equation, you have at least two natural choices. One would simply be to take a Brownian motion as you would do in the classical Feynman-Kac formula. But since we really only are interested in the one-dimensional distributions, you might as well take root t times a Gaussian random variable, centered standard Gaussian, and that would do just as well. And for the wave equation, well, it's a little bit different in each dimension, but let me focus on dimension 3, which is the one we're most interested in. And in that case, you would simply take t times a random variable which is uniformly distributed on the boundary of a ball of radius 1. Okay, so x tilde t, you would sort of choose a direction at random in 3 space and then move at constant speed 1 in that direction. Okay, so this is a fundamental motion in our problem, which is related to the equation we're studying, since it's using this fundamental solution S. And now I'm going to take IID copies of this basic motion, so independent copies. And then the second ingredient that I need is another simple object, which is simply a rate 1 Poisson process, independent of these IID copies of the basic motion. And so this Poisson process jumps up by 1 unit at random times, tau 1, tau 2, etc. And so the idea now of the random motion that I'm going to use in our probabilistic representation is built in the following way. I start from some initial position, and then I move according to the first basic motion. And I do that up to the first time of my Poisson process, first jump time of the Poisson process. And then I take the second copy of my IID basic motion, and starting from where I was, I move in the direction given by that second process. And I repeat. So if I can get the whole picture up. Down here you have the times of the Poisson process and the Poisson process itself, moving up by 1 unit. You start at some position x, and you follow the first process. So in the wave equation, this is just you're moving in a fixed direction at speed 1. You wait until the first jump time of the Poisson process. Then you pick another direction uniformly among all possible directions, and from where you are, you move in that direction uniformly at speed 1. You wait until the second jump time, pick another direction independently of everything you've seen, move in that direction uniformly, and repeat. Okay? So this is a rather simple probabilistic object.
Do you rely on translation?
Yes. Though we could do without it, but anyway, in this case, yes. And so here now is the formula, which is sort of an analog of the Feynman-Kac formula. And I'm writing it initially in the case where the fundamental solution is non-negative, like the heat equation or the wave equation in dimensions 1, 2, and 3. Say a little bit later what happens when when the fundamental solution could have negative, non-degenerate negative part. And so we're looking at the solution of LU equals VU, so that was your question. So L being our operator, heat or wave or whatever. And now here's the formula. So U of Tx is given by expectation of something, and there's this exponential of t in front. And so what is going into this formula? Into this formula is W, which was the solution to the homogeneous equation with the correct boundary condition. So that's just a deterministic object. We have the fundamental solution S, or at least the total mass of that. And in the times here are the times between jumps of the Poisson process. We evaluate the potential V at each position where we change direction. Okay, so, and we put here t minus tau I, so tau I is the time of the jump, and x tau I is the position where we change direction. And then here we have tau nt is simply the last jump time before time t, and that's the position where the process is at the last jump time before time t. Okay? So a rather natural formula. In the case of the heat equation, this factor here, S, is simply 1. In the case of the wave equation, it's simply tau I minus 1. So this is a fairly nice formula that applies to all the equations I've mentioned.
Is it somehow generalization of you mentioned telegraph equation, and I think Kac used the Poisson process there. Is it correct to say that?
So it applies to that equation. It's not exactly the same expression that Mark Kac had. He had a different sort of expression. But you know, it's giving the solutions. So
because I mean, there's also works on derive equation. So where also people use the Poisson process. And when you on the picture there, you only the situation is that you only kind of move up or down, like zigzag thing.
Yes, in one dimension you're sort of zigzagging, correct. Yeah, so it's not exactly the formula that Mark Kac said.
No, I didn't say it. I say you can't even call it the generalization of that. So I thought it is that in the derive equation you have kind of an option going up and down. So you have like a random variable distribution plus or minus 1. While you, like in the wave equation, you have something much more sophisticated.
A little bit more.
Is there a way of recovering the usual time?
So yeah, there's various ways of going from this to the traditional Feynman-Kac. So one way is simply that in the Feynman-Kac there's an exponential. You can write the series for the Taylor series for the exponential, and then identify the terms which will sort of be related to whether n of t is equal to k and so on. So that would be one way. Then there's other ways.
But in the classical case where your operator is d over dt minus 1/2 Laplacian, I mean, you get the Brownian motion here. You have no Brownian motion at all.
So as I said, you could use the Brownian motion. You could use the Brownian motion for the x tildes, or you could use root t times a fixed Gaussian.
I see. So basically what you're interested in. Okay, so it's a different representation, a different stochastic process.
Exactly.
Okay, here.
Yes. Yeah, if you use Brownian motions, that's when you would relate it most naturally to the classical formula.
So you could, instead of this deterministic motion, you could use Brownian motion or whatever other stochastic process between the Poisson times.
Yes. For the heat equation, yes.
Yeah, for heat.
And one more question now. This question is that in your theorem here you have convergence for every x, or in some weaker sense.
For every fixed t and x, it's an equality. And I don't know if I should give a sketch of proof or not, but let me just mention that, as I said, we had a series representation for the solution, which was a completely deterministic sort of representation. And so on this right-hand side, I can put sum over k indicator of n of t equals k. So I can just look at the terms where the Poisson process at time t takes value k, or value m here as I've written. And so that again gives me a series. And then I just identify the terms of this series with the terms of the series representation I had before. Okay, so and how do you do that? Well, you check that for the term equals the zero term is the same. And that's sort of a direct calculation, because in the other case, the zero term was just the solution to the homogeneous equation W. And in the case n of t equals 0, this product is set to 1. And you also have the homogeneous solution W. And then you sort of check that there was a relationship between the term of order m and the term of order m plus 1 in the series representation. And you just check that there's the same relationship here between the jm and jm plus 1. And that's essentially using the Markov property of this construction. So, once you have the formula, it's rather straightforward to check that it's correct if you also have the series representation, yes?
Excuse me, I can understand your proof, but I have still a question, because when you construct your process, the first one, the Ecole, actually you do not construct, as you said, the law of the process. You use only one dimensional marginal.
Yes.
Still, for the other process on the other side, every time you are in between the gems of your Poisson process, you are not using the distribution of the two-dimensional. And here you seem to use the distribution of the process. I mean, in your expectation, there is.
Well, I'm only using it in this computation here, for example, at the particular time tau 1. So, that's a fixed time independent of the motion. I mean, it's random, but it's independent of the motion. So I'm only using the process at certain times which are independent of the motion, and they happen to be random, but since they're independent, it's like they were fixed. Okay?
There is a kind of mystery, even if I can understand the proof. Okay.
Okay, very good. So it's been published.
I believe you. But for instance, if you use the square root of t,
Yes.
You don't get the usual Feynman-Kac formula, do you?
Well, you get the solution. So the solution is also given by the Feynman-Kac formula. It's just two ways of getting the solution.
Same expectation.
Do you get another representation, for instance?
Excuse me?
Using the other process, not the Brownian motion, you can imagine you can get for the classical heat equation another representation.
Using the root t times normal.
Yeah.
And relate that to the classical Feynman-Kac. That I doubt, but I doubt it because the classical Feynman-Kac integrates along the whole Brownian path.
Yeah. That's exactly the.
Whereas here, the rest of the Brownian path, in some sense, is being picked up by the fact
So
that
you
these
should
taus
have a
are
new
random.
representation of the classical.
It's a new representation. And you could ask, is it numerically better or worse? And I don't know.
Okay.
This is just to say what to do in the case where the fundamental solution is a signed measure and not a non-negative measure. And so in that case, you have a Hahn-Jordan decomposition into positive part and negative part. And they have disjoint support, and you choose that support in a measurable way. And then you sort of count the number of times you've moved or this difference is in the support of the negative measure. And then you just have this extra factor here, minus 1 to the power ct, which is that number. And here you have the total variation measure instead of the measure itself. Okay, so this is just a slight variation. And I just thought I'd mention that.
So again, maybe trivial question, just if you can compare. On your green picture, if you consider the Hill equation, case 1,
Yes,
where your axes are Brownian motion,
yes,
then the green picture will be another Brownian motion, yes?
yes. True. Yeah, in that case you could use a single Brownian motion for the whole time.
But this will be also Brownian motion, yes, if you have the independence.
Exactly. True. Okay, thank you for these questions.
You can get the Brownian motion of the
One
Yeah, it doesn't have to have rate 1. I've sort of taken rate 1. You could take a different rate. So now I'm moving to stochastic PDEs. So I'm replacing the potential V by this Gaussian random field F dot, taking stationary initial conditions independent of the noise. The noise is Gaussian, white in time, spatially homogeneous. This function f has to be such that this actually is a covariance. And so in particular, it should be the Fourier transform of a non-negative measure. And if you want the equation to have a solution, then you need this condition to be satisfied. And as usual for stochastic PDEs, you write the PDE as an integral equation. So this is exactly like I was doing with the deterministic PDE. Here now is the stochastic integral with respect to the noise and the fundamental solution times u. So here's where you have to say which stochastic integral you're using. And it's always an Ito integral, but so if S is a function, we can simply use a Walsh, Martingale measure stochastic integral. If S is a non-negative measure, like in the case of the three-dimensional wave equation, which is not a function, then you can use integrals that I've developed or extensions of that, most notably by Nouillart and Claire-Sardagnons. And you might prefer to use other integrals like Hilbert space-valued integrals and so on. And as long as it's an Ito integral, it will give the same solution. And Louis Square and I have written a paper that sort of relates all these integrals and shows that the solution is the same. So if people are interested in that, we just finished it close to last Christmas. But the preprint is available on the archive. So you're sort of free to choose your favorite Ito type integral. And again, the equation has the same structure as the deterministic equation, so you'll immediately have a series representation. And now this will be a representation in terms of iterated integrals. So the zero term is again the solution to the homogeneous equation, homogeneous Iter wave equation. And then here you have the terms of the series, which are related now by stochastic integrals and no longer deterministic integrals. But just as before, you have a series representation here with uniform convergence in L2 of omega over Tx in a compact set, or even x in Rd2 in a compact interval. Okay, so we immediately have a series representation. And now I'm going to look at moments of the solution. So let me start with second moments. And the ingredients are going to be sort of what I had before with a slight variation. So again, I have a Poisson process, rate 1. I have the random motion that I previously defined previously. So remember, there was ID copies of a basic random motion, and you change from one motion to the other at the jump times of the Poisson process. And now let me make a second copy of that process, which uses the same jump times of the Poisson process, but independent spatial motion, so independent of the motions of x1. Okay, so I have two motion processes which make me change direction at the same time, but the motions are independent. Okay. Well, this is the picture. So you have here the jump times of the Poisson process. And then the motion x1, say, is the green one, starts somewhere, moves until the first jump time, changes direction, waits till the second jump time, changes direction. And the x2 process starts somewhere else, picks its own direction of motion, but changes direction at the same time as the x1 process. Okay? So I have now these two processes instead of just one. And they change direction at the same time, but they choose their directions independently of each other. And so here is the representation of the second moment. So say a product moment, or x could be equal to y, and this would be a second moment. And so this is given by this expression, which is close to the previous expression. It sort of looks like you've multiplied inside the expectation, right? There's the w, the solution to the homogeneous equation, appearing twice. It's evaluated at t minus the last jump time of the Poisson process before time t, at the position of x1 at that last time, and the position of x2 at that last time. And then here I have a product which looks like what I had before. But so again, here is the term S, the fundamental solution, total mass of that squared. And then here, instead of having the potential V, I have the covariance function, right? Remember, F is the covariance function of the noise, evaluated at the difference of the two positions where the processes are changing direction. Okay? So this is a formula for the second moment.
F has to be a proper function. It's not allowed to be
True. So I'm not sure what hypothesis I've indicated, but yeah, we're taking F to be a bounded function, for example. Yeah, so space-time white noise would not be covered by this. And I won't give too many ideas about the proof, except to say that, again, we're going to relate this to the series representation, which was a sum of multiple stochastic integrals. So, they're orthogonal to each other. So if you write u as a sum, u of tx as a sum, u of ty as a sum, multiply the two sums, in fact, you only get a single sum because of orthogonality when m is different from m prime. And then, again, you're going to derive a relationship between im and im minus 1. And you're going to here create a series by summing over the possible values of n of t. So n of t is an integer, sum over indicator n of t equals little m. And that will give you a term jm, and you're just going to check that this term is the same as the term im. Again, using a Markov property as we did for the deterministic PD. Okay, so once you have the formula, again, it's not so difficult to check that it's correct. As long as you compare with the series representation that is still written here. And now we can get a formula for higher moments. So let me put this formula up. So this is a moment of order n. So product moment of order n. We could have x1 equals x2 equals xn. So you have the u to the power n. And this is equal to this expression here. So this is an expression which might look at first glance somewhat messy, but when you've looked at it for a while, I think it has some aesthetics in it. Combinatorics. And so there's lots of symbols here, so I want to explain little by little the various ingredients that are in this formula. So there is a set ln here, which is simply the integers from 1 to n. And that appears down in these products. So this is just a product of n factors. And then there's a pn that appears, script pn, for example, up here. And that's the set of pairs of elements of 1n. So you have pairs with two integers each. And a given pair consists of two integers, generically denoted rho, and I'll list the first one, which is smaller than the second one. Okay, the pair is not ordered, but one of the integers is smaller than the other. And the set of pairs that contain a given integer L is P superscript L, which does not quite appear in the formula yet. And now, before we had a Poisson process, now I have a Poisson random measure. And so this is n sub t of A. A is a subset of the set of pairs, and t is time. And so simply for any fixed A, nt of A is a Poisson process with intensity cardinality of A. Okay, so for any subset of the set of pairs, I have a Poisson process with intensity cardinality of that set of pairs.
And how are these Poisson processes related? For different A's?
So it's a Poisson random measure.
It's a Poisson random measure, so it's okay. It's a Poisson random measure in T times
Yeah.
Pn.
So if the sets are disjoint, it's
Okay.
independent. And so you know, to understand this Poisson random measure, we sort of have two different pictures that are equivalent. So here's the first picture is this picture up here. So here I've simply listed the possible pairs of 4 elements. So I've taken n equals 4, say the fourth moment, and there's 6 pairs which are listed here. And then the Poisson times are the sigmas, sigma 1, sigma 2, etc. And at each time your Poisson random measure selects a particular pair. So these are the little x's that are marked. So at time 1 we've selected the pair 1, 2. At time 2 we've selected the pair 1, 3, and so forth.
What is NT of L? You define NT of subset of Pn.
It's coming. It's coming.
All the
You know, I'm trying to get into the formula little by little. So that will come. It's written here, actually. The second picture is simply to write the 4 elements of Ln, 1, 2, 3, 4, and then at a particular jump time, you select a pair by drawing this little segment from one pair to the other. So pair 1, 2 is chosen here, or pair 1, 3 is chosen at time sigma 2, and so forth. So these are two equivalent pictures, if you want. And the particular pair that occurs at time sigma I is written R superscript I and consists of 2 elements, Ri1 and Ri2. And then NT of L is the Poisson random measure evaluated in PL, PL being the pairs that contain L. So it's sort of counting the number of times I've seen a pair that contains integer L. Okay, and it has jump times tau L1, tau L2, which appear in the formula, right? If you look at the S tau Li minus tau Li minus 1. So these are the jump times of the process NT of L, which are some of these sigmas, but not all of them. And now I need spatial motions. Right? This is the Poisson process, or the analog of the Poisson process. There were also spatial motions. So now I need spatial motions. And so here I have independent spatial motions, like I had for the second moment. Right? There was an x1 and an x2, which changed direction at the same time, but the motions were independent. Here there's independence. And when does xl of t, so there's n of these processes, or nth moment, there's n of them. It changes direction at jump times of the Poisson process nt of L, and not at other times. Okay? So let me put this here. And the picture is this one. So I have my jump times of the Poisson random measure. So these are all the sigmas that are listed over here. But now these are also jump times of some of the nt of L. So this is a jump time of nt of 1, for example. and also of nt of 2. But not of nt of 3, because 3 is not selected here. And so at this time, processes 1 and 2 change directions, but processes 3 and 4 do not. And at this second time, which was the time where we've selected pair 1, 3, right? We've selected pair 1, 3. Processes 1 and 3 change directions, but not 2 and 4. And so on. So at each jump time, 2 of the processes will change directions, but not the others. Okay? And so the W is taking here the last jump time before time t of nt of L, the position of that process at that time. We have the covariance function, which is evaluated at the difference of positions when 2 processes change direction. So for example, I would have the difference of these 2 positions, or the difference of these 2 positions. So each time a pair changes direction, those positions are put into the covariance function and this difference. Okay? And then the S term is taking the time between consecutive jumps of nt of L. So the time between 2 jumps of process 1, for example. So that would be the difference of these 2 times, or the difference of these 2 times. Wow, so I think this explains the formula, and this is why I was happy to have 3 pictures. One picture would not quite have been enough. There we go. What time is it? Okay. So let me leave this last one up. I have to sacrifice one of them. Okay, proving the formula, I'm not going to say too much about that, except that it's sort of, again, relating it to the series representation. And if you write each term here as a series, you multiply out the series, so you have a multiple series. And then you compare these terms with terms you get by fixing the number of jumps of each Poisson process. So the nt of 1, nt of 2, and so on. And relating the 2 things, so it's slightly more involved than for the second moment, for example. But so I don't expect you to read this, but it's not that complicated. Again, once you have the formula, it's not so difficult to check it. And so this brings me now to the question of intermittency. So if we developed all these formulas for a moment, it was in the end to analyze the question of intermittency. And so now I'm back with the stochastic wave equation. I'm taking constant positive initial position and velocity. And I want the solution to exist. So this, right, there was a condition on the fundamental solution. If you translate that for the wave equation, it becomes this condition on the spectral measure mu. So remember that mu was the spectral measure of the process, of the Gaussian process. Its Fourier transform is the covariance function f, which appears in the formula of theorem 5. And so under these assumptions, the equation has a unique solution, which also has finite moments of all orders. Wow. Okay, so there's a unique solution. Finite moment. Now we'd like to analyze the behavior of the moment.
How does the solution, I can't read, is bounded, how does it behave in X? UT.
For fixed t,
Fixed
how does
t.
it behave in X? So it's a stationary process in X.
No. How is the regularity in X? Is it?
Ah, you mean like Holder continuity? Or?
So it is regular in X.
Yeah, so if you, again, in dimensions 1, 2, and 3, you have to work a little bit differently, but in all those dimensions, it will be regular.
So
Here I have f bounded, so f bounded makes it continuous and so on, since it's a covariance, so it will be nice and regular in X. So here's the assumption, f bounded. And so that forces it to be uniformly continuous. Its maximum is attained at the origin since it's a covariance function. And let me call alpha the value at the origin. And so here's the statement concerning the moment of order n. So the expected value of u to the power n is bounded by the expression that's here. So we have the v and v tilde 0 were the initial position and velocity, so raise that to the power n. And then n appears here in this exponential, and the value alpha appears also, and the time t.
So you start with u naught equal 1. Oh, that's the v naught. V naught.
V naught is the u0. U at time 0 is v0.
Okay.
V0 is, yeah, maybe it should have been u0. But anyway, this is the initial position. So say v0 could be 1. V tilde 0 could be 1 for
And V0 is an L2 function typically?
v0 is a constant.
Is it fixed?
So constant initial condition. This
You're
is
not
the same as in Carmona-Molchanov, for example.
But you could take it to be a function, can you not? V0? Or is that?
You can. So say if it was bounded by a fixed value, that would this would apply.
This will still be true, isn't it?
But analyzing intermittency with other initial conditions, even for the heat equation, is a bit more complicated. So I'll mention some work on that, not of mine, but of other people. But the initial paper was with a constant initial condition, and so we've done that also. And so this would give you this estimate on the log of the nth moment divided by t. So this is the upper bound. And again, when you have the, let me put that over here. When you have this representation of moments, it's sort of a combinatorial analysis of this Poisson random measure and so forth to check the formula. But in the case of the second moment, it's a little bit easier, and I just want to explain that. Okay, since here the calculation is comparatively simple. And so we want to show this inequality here. So with the n equals 2, you take the formula over there with n equals 2. And then we have this representation of the second moment. So this is the representation with the two motions that jump at the same, that change direction at the same times, and so on. And so W is simply the solution to the homogeneous wave equation with the same initial condition. So if we start with a constant value v0 and a constant velocity v tilde 0, after t units of time, you will not be greater than this value here. There's w times w, so that comes squared. There's this exponential of t, and then there's what's left inside the expectation. So in the case of the wave equation, this quantity s, total mass of s, is simply tau I minus 1, so that's appearing here squared. And then the covariance function we've bounded by alpha, so that's appearing here. And so again, we're going to condition inside this expectation at the first jump time of the Poisson process. And so out comes one factor, and then we're left with another factor, which essentially looks like what you had before, but you just have less time remaining until the final time t. And so if you write what's random here now is the jump time of the Poisson process and the position where you're at that time. And so you simply integrate against the the exponential density of this random time, and s squared is tau 1 squared, so tau 1 equals s e to minus s ds, and this is simply the same function h, but now you have less units of time. You have t minus s units of time. So now I have an equation h of t equals this expression here. And this is not quite a standard differential equation, but you can work at it a little bit, solve it explicitly, and then you just have the bound comes out. Okay, so it's a linear equation, so you work a little bit and you solve it. So that proves the upper bound, at least in the case n equals 2. And then the work on the lower bound is separate, again using the formula we have for the nth moment. And so here, I have an upper bound on the covariance function f in my previous assumption. But if I want a lower bound on this moment, at least I don't want f to be identically 0, for example. My covariance function here is non-negative. So I want there to be a region where it's strictly positive. So a region in the, centered around the origin. And so it's going to be bigger than alpha 0, some positive constant, near the origin, at least, so that the noise is not degenerate. And then we have a lower bound, which looks essentially like the upper bound, but with different constants appearing. Where does delta appear? Probably in the constant c, right?
No, because you said there was a universal constant.
Good question.
How universal is universal?
How universal is universal? No, if it says universal, it should be universal. I'll look into that. But, yeah, I don't know. It should appear somewhere, you're right. Okay, so this would give you the lim-inf log expectation of the moment, nth moment over t, bounded below by an expression similar to the one we had before. Of course, we haven't quite checked that the Lyapunov moment exists, right? That this limit exists. But if it did exist, then we would have strict inequalities infinitely many times. So the upper and lower bound together imply that you would have strict inequalities in infinitely many positions, and which would be an indication of intermittency. But sort of the subadditive ergodic type argument, which gives existence of the Lyapunov exponent for the heat equation, we were not able to make work here.
Erase?
Oh, sorry. Yeah, so these inequalities you have, but they could simply be equalities, and they could all be equal to 0, but the statement is that there's infinitely many of them that are strict.
Those are lambda ones? I see that's the limit. If the limit
If
exists.
the limit exists.
And you can order them like this, right?
They're always ordered like this. Voilà, so that's what we've done. And now a little bit of so references and other work. Voilà, so the first two papers are the ones that I've been presenting. So the paper with Carl Mueller and Roger Tribe appeared in Transaction of AMS. So this is the Feynman-Kac formula and the representations of moments. And then these upper and lower bounds are in this paper that came out in Annales de l'IHP. And I've just listed here some other related work. For example, Backlund and Mueller also give a probabilistic representation for a nonlinear wave equation. Okay. Right, we have a semi-linear sort of U times potential, whereas they have given a representation with a fully nonlinear right-hand side. And then this recent preprint of Konus and Koshnevizan, so 2010, meaning came out a week or two ago. Here they look at the one-dimensional wave equation, and they show that the Lyapunov exponents do exist, and they give some information about where these high peaks are located. Okay, so this is a recent paper which sort of gives this picture of high peaks, or sort of some information about that for the wave equation in dimension 1. I've mostly talked about dimension 3, but of course our work also applies to dimension 1. But this is a slightly sharper analysis specific to dimension 1, at least for the moment. There, thank you very much for your attention.
About this intermittency, the definition of it was that there is a number at which one of those expressions is 0. You don't have 0 because everything is non-negative, yes?
It's all non-negative, yes.
So there is no intermittency according to your original definition.
No, intermittency is that
Is that at some point it becomes strictly positive. They're all non-negative.
So intermittent is
It's
not
not
that it's negative, the transfer, but at least from some moment it's positive.
Yes, exactly. And so that will happen.
And
it's not massively above equal.
that was my question. Yes. Okay. And another question, if I can, is that everything you've done here for fixed t and x, and maybe follow from this. But what about some norms with respect to x? Somehow,
You mean like the L2 norm? Weighted because it would be infinite if you just put the Lebesgue
Is
measure.
it just the same?
No, I don't know the answer to that question because, so you have to put some weight, right? But
Yeah.
then you're sort of measuring how much mass is contributed by the high peaks. And so you would be, I think Cranston and Molchanov have information about that for the heat equation, for example. So how much of the mass is coming from the high peaks if you measure it in a certain way. Yeah, so they were with discrete space and sort of summing or averaging over a sizable region. That's sort of close to what you're saying. But yeah, I would not directly have information like that here. I mean, typically what happens if it's a very small region, then it's just like at one point. But if it's a big region, then the situation changes. Right, so the size of the region and how this region grows with time affects the limiting behavior that you would get.
You have this Ecole is about the joint moments of the random field UTX for fixed t. So can you at least formally translate that into some formula for finite dimensional distribution? No, I mean, I don't know.
No, that's a good question.
Algebraically, whether, things work
So, we didn't think about that, but that is a natural question.
No, but I mean, if I take these things and sum them up, I mean, there's a nice formula, perhaps I can come up with something.
Yeah, I mean, certainly you have the series representation, so you can take that at different times and positions and multiply that out. So I wouldn't be surprised that something like what we did could be...
But you have fixed time, not different times.
No, we have fixed time, but you would simply start the motions at different times.
Okay.
Yeah, so I would imagine that that should be doable, but we haven't done it.
So the constants, little c and big C, are actually constants. They do not depend on x, right?
No, they do not depend on it.
So you have a sharp, in terms of the growth, is
Yeah, it's
they
sharp.
look the same, isn't it? The upper bound and lower bound are
Correct.
the same nature, so to speak.
Yeah,
Which is
yeah,
interesting.
no, we're happy with that.
That's great. So you, at the beginning, you said that you consider many examples of equations which have this assumption about the fundamental solution. But you, at the end, you spoke about the wave equation. So but also the formula, Feynman-Kac formula for general. So do you think that similar results can be proved by similar methods or other equations?
Well, so
Okay.
we were happy to get this.
No,
and then we-
I was not criticizing.
No, I appreciate
Asking about
it.
your,
No, it's natural. So the only other case where we tried to apply this method was the heat equation, just to see that we would get back the results of Carmona and Molchanov. And actually, they did it for discrete space. So this gives it for continuous space. So it's a slight plus, if you want. And then we did not try to look at the other equations for which, in principle, you could use these formulas. Yeah, so, the wave equation is nice because the S of tau I minus 1 that is here is just this time difference, tau I minus 1. The heat equation is easier because the S is just 1, constant 1. It's actually a little bit easier. And then, for another equation, you would have to analyze the behavior of this term. And I can imagine that you could try that, but we have not.
Okay, so let's thank Prof. again
Thank you.
very much.